Okay. So, to answer this question, let us now look at routers in practice, how they are designed, okay, what is their architecture, and once we understand, we will also look at the evolution of a network processor, and finally, after we look at the evolution, we will see the architecture of a network processor, and once we look at the architecture of a network processor, then we will look at how to improve the performance of a network processor along with the architecture. That is the goal. Okay. I hope this introduction will help you now understand the slides that are going to come. Okay. So, let us look at how the internet is organized. Okay. You start off with a LAN network, that is something like this, a business or a residential Ethernet that starts something like this, and then these networks connect to something known as aggregation services router, okay, ASRs, okay, and they connect to bigger aggregation services routers. So, if you look at this, these routers are slightly small, they connect to routers that are slightly larger and they have more excess capacity, I mean, than these routers, and then these connect to core routers. So, this is known as access, edge, core, okay, and these routers increase in size, they consume more power and so on. Say for example, and the architecture of these routers are also different. Okay. Essentially, as the routers increase in size, you have more amount of parallelism and pipelining that will come into picture. In essence, any network processor architecture has number of pipelines and operating in parallel. Okay. The advantage is why we can do that is because packet size more or less in many protocols are defined. Okay. Because of that, you can actually design processors which can cater to that specific packet size. Okay. So, for example, a word length is 32 bits and the IP address IPv4 at least is 32 bits. Similarly, IPv6 is 128 bits. So, they fix the packet sizes. Okay. Because of that, you are able to say byte boundaries and all that. See, remember one of the things, ATM had 53 bytes, but in your architecture class you always talk about byte boundaries, byte boundaries. Now, 53 bytes, how did they land up with 53 bytes? I mean, it was more political, but anyway, I mean, they landed up with 53 bytes, and the processing time actually would have taken a hit if you process 53 bytes at a time. Okay. Anyway, so coming to this, so if in these kinds of routers, okay, as the router size increases, one of the things that they do is, if you look at this diagram, you see some kinds of, these are known as line cards, okay, those stuff that are here are known as line cards. Each line card has many network processors. If for a smaller router, there will be one network processor, but as the router sizes increases, there will be more network processors. Similarly, for a smaller router, there will be one line card, as the router sizes increases, there will be more line cards. And these line cards will be interconnected at the back through a switching element. Okay. So, this is in general the architecture of a router. So, the router has, so from whatever discussions we had until now, you know that a router has to have a regular general purpose processor, it needs to have a specific network processor, and all these things must operate at high frequency, parallelism and pipelining must be implemented. Okay. So, let us see how routers have evolved over a period of time. In the 1980s, when the first router was made by Cisco, okay, they took a normal computer, okay, look at this, it had a CPU, it had a DRAM, and then it had flash, NVRAM, and then console, and then auxiliary ports, etc., which is normally what you get in your regular PCs. Okay. The only thing extra that it had was the interfaces which connected different computers. So, a data packet used to come here, okay, the packet will be given to the CPU will do all the operations, store it in memory and then do all the operations, and then again it will route back into the interface and the data will go out. This is the first generation routers. Okay. The second generation routers, what happened was the CPU started having process switching was implemented, the Linux operating system, okay, multiprocessing systems. Okay. So, what happened was, instead of processing one packet at a time, as soon as I start receiving a packet, I can give it to one process, the whole process will do all the operations and then send it to the other machines through the interfaces. So, this was the next improvement that was there. Okay. So, it is I mean it helped in actually real time packet processing, because as soon as the packet is received, you can just forward it to a process and then everything can be taken out. I mean it is not that every packet will be processed using a process. At least you can, if you have more than one Ethernet port, one port can be completely dedicated, and I mean any data packets that arrive on that port can be buffered and given to a process. I mean you can do all those things in the OS. Okay. Then the next level, okay, because they wanted increase in performance. So, what they did was, whenever a packet used to come to the system, they used to actually generate an interrupt. Okay. And if you remember, in Linux, interrupt has a top half and a bottom half. Okay. That is, once the packet is got, okay, the packet is actually stored in a DRAM, okay, and then the interrupt service routine returns. Then a process picks up that packets and then performs the necessary operation. That means you have to process the packets quickly. So, as soon as a packet comes, an interrupt will come. Now, the packet is taken, put in memory, and then the interrupt service routine will return back. It is up to the process to process the packets. So, in this case, if you look at this, the control packets were taken by the processors, okay, and the data packets were retained in the IO region. Why? Because if we take from IO region, go to memory, again come back to IO region and then encapsulate the packet and then send it back, it is going to take a lot of time. So, what I do is, I just split the packet into control and data. The control packets alone will go into the processes for processing, because any data packet, if you remember the first slide that I showed, only the headers were added to a data packet, and the data packet did not change. So, why can't we just store the data packet in one place, take the headers alone, do all the processing and then attach a new header to the data packet and send it. That is the idea. Okay. In that way, they were able to get much more speed up, and actually the process 7200 from Cisco. Okay. I am taking Cisco as an example because they actually occupy about 70% of internet routers. So now in this way, okay, so the memory was divided into two regions. One is for the process region, the other is for the IO region. Okay. So, this was the next level of, so in this case, this was the time where the data plane versus the control plane were split into two. And remember, the data plane needed a general purpose processor because it was running algorithms. Sorry, the control plane needed a general purpose processor because it was running algorithms. The data plane needed fast transmission of data packets. Okay. Now, the next generation. So, what was the problem there? So, the problem was that when I take this guy out and then put it in the control packets were put here and then the IO region was here. Okay. The next level what I see is, look at this, this is the data packet was sent to DRAM, there was no problem. Okay. And then this control packet had its own operating system, because the scheduling, see for example, when the internet was started, okay, people never conceived that voice will be a part of internet or video will be a part of internet. They only talked about FTP, telnet, etc. But over a period of time what happened, voice came and video came, and because of that quality of service became a major factor. Now, if you are going to run a general purpose operating system and then try to get quality of service, you are in for trouble. Okay. So, they had to have a specific operating system to take care of quality of service. Okay. Especially how does quality of service get affected? Because of buffers and timings. If you have more buffer, then it delays the packet, and because of delay, you know, quality of service depends on jitter and delay, straightforward. So, now that I have buffers, when I take more time to process my control packet, for that much time the data packet has to sit in my DRAM. Okay. And not only that, if I delay processing my control packet, my data packet also gets delayed. So, in order to avoid this, they wanted to come up with better scheduling algorithms. So, they put a small operating system, okay, next to the CPU. Okay. So, then the next speed up that they tried to achieve was, because this process you have to switch, you have to take the control packet out and then give it here, and then the data packet out and you have to give it here. They put some ASICs because the network speeds were increasing. Okay. So, they could not process these things at that speed with their general purpose processor. So, because of that, what they did was the data packet speeds were increasing. So, they put a ASIC, the ASIC will do the switching very fast, okay. And not only that, it had control memory. What is this memory? See, once I calculate the routing, that from which port I have to put it into which port, then I have to store that information. Okay. So, I calculate all those things in the CPU, then I store this information here, so that when a data packet comes, I need not send all the data packets to the top, I can do some processing here and then put it in the, for example, I get a data packet from in a line card from one port and I want to send it to another port in the same line card. Why do you have to go to the processor to calculate it? Because the line card has all the details. Okay. So, in that way they have to improve the processing speed. Then now came the requirement for network processor. So, once you started doing all this, so people thought that, okay, now that I have put a ASIC here, why can't I put a processor there which will take care of switching very fast, okay. And not only that, this also has to provide a traffic manager, as I told you, for controlling the buffers, queuing and scheduling. So, 3 operations it has to do here. One is buffering the packets and then queuing them, putting it in, because the packets can have priority, okay. And then what to schedule, which packet has to be sent first based on the priority, okay. So, what they did was they put a network processor here, okay. So, they call it as the network processing unit. We will see what goes inside later, but then at the highest level let us see what they are doing. So, this did a traffic manager, okay, and this handles the direct memory access and queuing of complete packets, okay. And then the network processing units looked at the forwarding lookups and operations. So, this relieved the CPU, the general purpose process, of task of that forward lookups and say for example, remember when we got a packet, we have to match the destination address and then send it, okay. So, the network processing unit took up that job rather than the CPU itself trying to participate in that general purpose processor, okay. Then what happens? So, this was the control plane architecture, okay. So, what they did to the data plane, okay. So, now what happened was, if you look at this, the data plane architecture, the centralized hardware router. So, what they did was they integrated the CPU, the general purpose CPU and the network together. It had its own RAM. Look at this, the CPU had its own RAM and it controlled the peripherals, okay. And the network process had its own packet DRAM and it had control memory. So, if you look at the difference between these two, this OS that was there actually moved into here, the network part of it, okay. So, instead of running the OS in the general purpose processor, they just moved it to the network processor. So, then the advantage of this is, so if you look at the data plane never goes to the CPU, does not need any CPU for any operation, right. Only the control plane needs a CPU, okay. So, the data plane actually was handled by the network protocol part of it, network processor part. So, if you look at this, only the control plane has to go here, the data plane stops here. So, therefore, what they did was they took the data plane, this is how the data plane is, and that is one of the reasons they came up with line cards and then they had a route switch processor and so on, okay.
One question.
Yeah.
Yeah, as you were explaining the evolution, any specific advantage for NPUs over the ASICs?
Specific advantage of NPUs over ASICs. Yeah, I will come to that, I will answer that question at the end, because now I am just introducing you what are the components and how they have split this NPU and all that. Once we complete, when I come to performance, then I will tell you why we need ASICs, okay.
Yeah, no, because your slides were, showing the slides in a sequence as an evolution. So that's why I just asked.
Yeah, that's right. But you will understand why we go for NPUs. See, ASICs are usually used for switching. Okay. So I'll tell you why ASICs came into. See, initially, yes, they were just switching the packets. Therefore, they were using ASICs. Okay. So later, what happened was they wanted to handle this buffers and other things. At that time, switching just may not be enough. You need a processor and you need to store the packets before you start sending those packets out. Okay. That is where they brought in NPU, network processor unit. Okay. Does that answer your question? Okay. See, initially it was only for switching. Okay. Then you had to buffer. Therefore, they brought NPU. Okay. Fine. So let's proceed. So see, one of the things that you should see from this slide is, see, the data packets, if you look at this, they need not go into the CPU. Okay, so what you can do is, you can just take the data packets from the interface and then you can just get it back into the interface again without going into the CPU. So that is, and this can be done very fast. Okay. Now what happens if you go to the CPU? Okay, let's take for example a traffic manager. Okay, so I told you during the jet the delay and jitter gets affected. Now how does jitter get affected here? So for example, you are using some sort of a scheduling algorithm in CPU, right? So if the CPU is involved in transmitting the data packets, the CPU will do it based on, I mean the OS that is running on the CPU will do it based on what type of scheduling algorithm you are going to use. Now it is never going to be first come first served. Okay, if it is first come first served, then you can to some extent expect that the data packets will have the same jitter, but you can use any type of scheduling algorithms. Okay, so that is the reason. Okay, they really wanted to move these things out of the CPU and give it to a special network process. Okay. Now one thing that happened was, now with a network processing unit and a traffic manager into picture, this device itself was capable of handling more data traffic. Okay. So instead of having just one interface and then using one network processor to handle that interface, what they did was, they did something like this. The interface became independent of the processes. Okay. If you look at this, here the processor and the interface were all connected together. The CPU, the processor, the network processor and the interface were all connected together. If you look at the next evolution, they just removed the interfaces and the interconnect together, because what they were able to do was, they were able to receive data packets at a higher rate from different interfaces and then pass it on to the network processors, and these network processors did all the calculations and then sent it to this. So these were called as port adapters or shared port adapter or SPA interface process. Okay, they called it. Okay, so Cisco's products like 7300 and 10000 actually use this kind of an architecture. Okay. Now with this, the advantage is you can bring redundancy. That means I can have more than one interconnect. Then I can also bring in fault tolerance into this network, because if one interconnect, this card fails, I can put another card and then the whole thing will work. Okay. So this is the next architectural improvement that they did. Now after that, what happened was, see, they divided. So look at this, then they put one more dash, split it one more here. I can have one route information, route processor, I can have many forwarding processors, and I can have many port adapters that are connected to the forwarding process. That is the next improvement. Now, as I told you, this is the way they actually, what is this architecture? Is it parallelism or pipelining? They try to bring in more parallelism. Okay, the hardware parallelism. Okay, so in this case, if you see, the CPU had a route DRAM and a peripherals that it controlled. Okay, and then the network processor had now this was named as the forwarding processor, because what happened was the data packets came here and then it looked into the table and then it routed the packets to the interconnect. Okay, and now they had more than one. So, if you look at even today in hub and all that, you have 8 port hub, 16 port hub and so on, right. Similarly, these are the interfaces, that ports. Okay. So, you could have say 256 port device, okay. It will just be a line card, okay, and that will be connected to a single NPU or a bunch of NPUs. You can do, so you can have variations architecture. Remember, I showed you the architecture in the first diagram, okay. Then what happened, okay. So, what happened here is scaling the forwarding path, okay, parallelism with network process. So, the network process themselves were, so if you look at this, instead of having one network processor, they had multiple network processors here, okay, and they were connected by a integrated circuit, okay. So, essentially if you look at this, and then the route processor was relieved of all the burden, okay. So, there was only a small route processor, a single route processor, and then as a forwarding process they had, and then you had this interconnect. So, if you look at this next stage of evolution, I had only one, now I have many, they are interconnected, parallelism at the next level, okay. Then what happened, okay, sorry, okay. Then what happened, okay. Then they introduced, see, because they had to communicate between this networking process and this RPU and then this interconnect and so on, they actually introduced a switching fabric, okay. And this switching fabric they called it as a back end, they put it at the back end, so that I can put these guys in a card, I can put this guy in a card, I can put these people in a card, and then I can connect all of them using a switching fabric that operated at high speed, okay. So, in this case you have a centralized forwarding, but distributed memory. Centralized forwarding because you are using this network processor and route processor etc. together, and distributed memory because each one had his own memory, okay. So, the Cisco ASR 9001 which I showed you in one of the slides, which is the, so had this, and then the next level, okay. You had many CPUs, okay. You had many interfaces and each interface had its own network processor and all of them were connected via the switching fabric. So, if you take this guy alone, he will act as a router, this guy alone he will act as a router, as a switch, this guy alone he will act as a switch, and this guy alone he acts as a router. So, each one, so here you see there are two. So, this is massive amount of parallelism, I mean they call it as the distributed router architecture, obviously because like distributed computers, okay, each one was self sufficient on its own, and architecture like Cisco 12000 etc. followed this kind of an architecture, okay. So, when you compare with general purpose process, you have, I mean you have this application, okay, IO optimized process and then integrated acceleration, then you had software library, integrated external access. So, if you go with general purpose process, this is the way they grew, okay. And for networking, okay, they had multi-core and all those things, instead of having a single network processor, they had multiple network processors and so on. So, essentially it is a kind of parallelism, but remember as you increase the number of processors, you have to look at power, okay, and security. Okay, so, until now we have been only looking at the architecture, not security and power. So, here is the question that was asked. So, why should I need a network processor? Why can't I go with ASICs? So, this answers the question. Okay, this slide actually answers that question. So, look at this performance versus flexibility. So, if I have a CPU, okay, you can have multiple processors etc. and these general purpose CPUs are used in access routers. Okay. If I have an application specific IC, okay, you have very high performance, okay, whereas a network processor is in between a CPU and a ASIC. See, ASICs actually cost you a lot. Okay. So, in order to achieve a balance, and CPUs, I mean general purpose processors are actually very cheap. So, this NPU actually lies between these two. Okay. So, now that, so if you look at this, network processors are used in say edge routers and aggregation routers and then core routers, and then application specific ICs are used in switches, okay, layer 2, okay, and network processors are used in layer 3 usually. I mean, it's but not a strict rule. Okay, if you are a hardware guy, I mean, you can sell it in that way. Okay.